In this talk, I'll present a sublinear local access implementation for the Chinese restaurant process. This is joint work with Peter Mertos and Christian Sohler. I'm Stefan Walzer. To understand what we mean by local access, imagine a setting with two players where Bob knows a huge random object X and answers a sequence of adaptive queries about X issued by Alice. So for instance, Bob might know an Addish-Rainey random graph, and Alice asks, say, whether X contains a certain edge, or she may even ask for the entire set of neighbors of a given vertex U. So imagine now that X is extremely large, so that Bob cannot actually afford to generate X completely. However, he still wants to have this conversation with Alice, and Alice shouldn't be able to tell the difference. The idea is now that Bob only samples those parts of X on the fly that are relevant for Alice's queries. A bit more precisely, the service that Bob wants to provide is that of a local access implementation of X, sampled from some distribution D. This means two things. Firstly, the distribution of Bob's answers must be as though he were really responding to queries about X. And secondly, the time it takes Bob for pre-processing and to answer any of Alice's queries should be polylogarithmic in the size of X. So consider, for instance, this neighborhood query here. In an Addish-Rainey graph, such an answer depends on n-1 independent random variables, one for each potential neighbor. But if we were dealing with sparse Addish-Rainey graphs, where the expected number of neighbors of U is constant, then there are tricks to generate an answer in polylogarithmic expected time. Local access implementations in this sense have been achieved by various authors in the past. So for example, for Addish-Rainey random graphs as suggested, even for dense ones and the stochastic block model, but then without an all neighbors query. For Catalan objects, for preferential attachment trees, and for random walks. And in this talk, we'll make a new addition to that list, namely the Chinese restaurant process. The Chinese restaurant process is a well-known discrete time stochastic process, where at every point in time, there's a sequence of tables, and at every table, there's a cyclic sequence of customers, which are numbered from 1 to n. And at time step n+1, a new customer arrives, and he sits down in any of the gaps between the previous customers, as indicated by these arrows, or he may open a new table where he'll be sitting alone for now. And in the easiest case, he makes each of these n+1 choices with equal probability. So let's say this customer decides to sit between 3 and 5, then the new state will be this one. Then customer number 14 arrives, and he has a similar set of choices, makes each of those with equal probability, and so on. In the paper, we also consider a setting where the tables have assigned fitness values, and the spots on the tables with large fitness values are more attractive than the spots with on the other tables, and where a newly generated table is assigned a new fitness value according to a distribution phi. But not much is lost if in this talk we focus on the easiest possible case without these fitness values. So in the following, I'll use a slightly different representation where the tables correspond to rows and are no longer drawn cyclically. With the slider here, I can step through the process. In the beginning, the restaurant is empty, and then through the process, customers start new tables and join existing tables, as discussed. Right, so why is this process relevant? Well, to throw some keywords at you, in particular with fitness values I talked about, it's closely related to the Polya-Earn model and Dirichlet processes. It models rich-get-richer dynamics, because tables with many customers tend to gain additional customers quickly. This makes it useful to, for instance, model gene expression data in bioinformatics. And moreover, the fact that the number of tables over time is a random variable, makes the induced partition of customers into tables suitable as a prior for clustering tasks where you don't want to choose in advance how many clusters to use. But don't worry if none of this means anything to you. In this paper, we're far from any concrete application. We just want to implement a local access implementation. This means we want to be able to answer questions like these. What's the size of table 2 at time 10? So, well, it's 5. Who sits to the right of 1 at time 15? Well, it is number 9. And when is table 3 created? As you can see, it's created in step number 13 by customer number 13. So remember, we want to answer an adaptive sequence of such queries in polylogarithmic time, that is polylogarithmic in the largest time step that queries may refer to. So for the first part of the talk, I'll consider a simpler setting with anonymous customers. So then it no longer makes sense to ask who sits to the right of somebody at a given time, but we can still observe how the sizes of the tables evolves over time and when new tables are created. Speaking of table creations, let X be the set of time points when table creations occur. Then this is the probability that at time step I, a table is created, which is just 1 over I. So you can see that the expected number of tables overall is just the nth harmonic number, so it's not very large. And it's actually easy to sample this set X. Let me show you. So n is the number of steps for which we observe the process, and every number I up to n should be included in X with probability 1 over I, independently for all I. And how do we do this? Well, we start by sampling a random number between 1 and n. Say it's 8. We include that in X. Then we sample a random number between 1 and 8 minus 1. Say it's 5. That goes into X as well. Then a random number between 1 and 5 minus 1. And so on. And we keep doing this until we have included the 1 in X. And a simple induction shows that this algorithm really samples X with a right distribution and in expected logarithmic time. So if figuring out when tables are created is not so difficult, let's focus on what we don't yet understand and start with a fixed number of tables and condition on no further table creations occurring. Here on the right, I show the probability that the next customer will join the respective table, which in general is just the number of customers at that table, so like 1, 6, and 2, divided by the current n. Let me recall some fundamentals you've probably seen before. Let's say Alice and Bob have gone fishing, and Alice is a bit better at it, so she catches fish with a rate of 4 per hour, while Bob catches fish with a rate of 3 per hour. It's still random though, so formally this is described by Poisson processes with parameters 4 and 3. In particular, what has happened in the past does not affect what's happening in the future. And in even other words, the delay delta A until Alice catches her next fish has exponential distribution with parameter 4, and for Bob it's the same with parameter 3. This means then that together they catch fish with a rate of 7, meaning the minimum of delta A and delta B has exponential distribution with parameter 7. And moreover, the probability that Alice catches a fish before Bob does is 4 over 7. And this can be generalized. So if I have several exponentially distributed random variables with parameters lambda I, then the minimum of these variables also has exponential distribution with the sum of the parameters, and the probability that the ith variable is the smallest is simply proportional to lambda I. Now consider a simple birth process that starts with a single token at time 0, and then when it has I tokens, gains the next token with a rate of I. And imagine that the tables here, instead of gaining customers as explained earlier, are governed by independent simple birth processes. So this table here gains the next customer with a rate of 1, this table with a rate of 7, and this table with a rate of 2. Now, by what I've said on the previous slide, the probability that the next customer will join table 1 or 2 or 3 will just be 1 over 10, 7 over 10, and 2 over 10, just as it was previously. So the distribution of the sequence of states generated in the old view and the distribution of the sequence of states generated in the new view is exactly the same. The only difference is that the new view lives in continuous time while the old view lives in discrete time. And a bit of work is required to translate queries concerning one view into queries concerning the other view. But the great benefit is that in the new view, these tables are independent because this description up here and the rates here do not mention the other tables at all. The thing left to do now is to obtain a local access implementation for the simple birth process. So for an adaptive sequence of query times t, we should report quickly what the state of the process at those times is. And I'll shift to a slightly different process known as the simple def process, which starts with n tokens at time 0. And when we are in the state with I tokens, we transition into the state with I minus 1 tokens with a rate of I. Compared to the simple birth process, there's a plus minus 1 issue going on, and we have to know in advance the number of tokens n with which we start. But otherwise, the simple def process is just the simple birth process played in reverse. But there's an alternative view which is useful. Namely, we can imagine n tokens have independent lifetimes drawn from an exponential distribution with parameter 1. And then the simple death process is just the number of tokens surviving until time t. So this matches this description up here, because if we have I tokens remaining, then they independently decay with a rate of 1. So together the next event occurs with a rate of I. Let us now simplify the problem further. So here we see the function e to the minus x and a bunch of x values and corresponding y values. Then saying that the x's are independent with exponential distribution is equivalent to saying that the y's are independent with uniform distribution in 0, 1. This is not true for any density function, but it's true in this case. And then the simple def process is equivalent to an even simpler process here, where we sample y's uniformly from 0, 1, and where instead of asking how many x's are above a certain t, we ask how many y's are below a certain u, where u would correspond to e to the minus t. So we now only need a local access implementation to this object, meaning for an adaptive sequence of query values u, we should answer with p of u, doing so in time that is polylogarithmic in n. And for this, we imagine this infinite tree corresponding to a recursive partition of the unit interval. So the root is annotated with 1/2, the left subtree is responsible for the interval from 0 to 1/2, the right for 1/2 to 1, and so on recursively. So this means every number between 0 and 1 corresponds to a unique path in this tree, and a uniformly random number in 0, 1, like those y's, correspond to a random path that takes a left or a right at every step with probability 1/2. Okay, and let's now say we have a query for 0.37, which corresponds to a path. And the idea is now to determine for every node on this path how many of the y's also go through this node. So if n is 20, then all 20 of the y's go through the root. But how many go left? Well, this has binomial distribution with parameter 20 and 1/2. So we sample this, and let's say the result is 7. And then the next question we ask is how many go through this node? And again, this has binomial distribution, now with parameter 7 and 1/2. And we sample that as well. And we go on sampling like this until after an expected logarithmic number of steps, we have a 0 on our path. And then the answer to the query is simply the y's that have somewhere taken a left where we have taken a right. So here the answer is 2 + 2 = 4. Say we have another query now for 0.81. Then we do the same thing again, except that we don't start at the root because we already know 13 go here, and we start sampling at this point, refining the annotation as is required to answer the query. Here we get a 0 at this step, and the answer to the query is 7 + 9 = 16. So this concludes the argument that we have a local access implementation to this object, except for 2 remarks. So one remark is that I lied. So actually you have to stop walking along the path when you find a 1. This is due to an issue with adaptive adversaries, and it's easily fixed. And the second remark concerns how we sample binomial random variables in polylog time. And there we just use a result by Bringmann et al., which conveniently proved that you can actually sample binomial random variables in expected constant time on a web RAM. Recall that so far we've been ignoring that customers have IDs. Let's stop ignoring this now. And let's instead pretend that there's just a single table. So over time, we always have this single sequence of customers, and when a customer joins, he joins the sequence in a uniformly random position. In the end, this gives us a uniformly random cyclic permutation, and local access to this sequence here would not be difficult to provide. But it's not quite sufficient. For instance, we want to answer a question like who sits to the right of 3 at time 5. And this conceptually requires scrolling back in time to see here that the answer is 2. Of course, the final sequence still contains this information, but we have to skip over every customer that is bigger than 5. And doing that explicitly would take more than polylog time. So to solve this problem, we represent the same information in tree form. So this tree is also obtained as a process. And let's say when a customer X sits down to the right of a customer Y, we add X as the leftmost child of Y. So to give you another example, customer 11 sits down to the right of 6. So 11 is prepended to the child list of 6. The sequence up here is just a pre-ordered traversal of this tree. And since the tree has logarithmic depth and logarithmic maximum degree with high probability, local access to this tree implies local access to the sequence. The earlier stages of the sequence correspond to earlier stages of the tree, and these are simply obtained by ignoring subtrees with too high IDs. And ignoring these high IDs can be done efficiently, again due to the logarithmic maximum degree property. And along these lines, we can argue that all we need is local access to the final state of this tree to obtain local access to the earlier states, to obtain local access to the earlier states of this sequence as well. And I'll briefly sketch how we can do this, but I should mention first that this has already been obtained by Evan et al. In an earlier paper. A random recursive tree with n nodes is given by n-1 random variables that indicate for every vertex what the parent of that vertex is. So here's a possible outcome where the parent of 9 is 5, and well, every variable attains each of its possible values with the same probability. So how do we provide local access to such a creature? Let's say the neighborhood of vertex 4 is requested first. Then the parent of 4 is simply uniformly distributed in 1, 2, 3. That's easy. Let's say the result is 3. Concerning the children of 4, 5 is a child of 4 with probability 1 over 4. 6 is a child of 4 with probability 1 over 5, and so on. Yeah? And earlier I've shown you a trick that allows us to sample a set X that contains each I with probability 1 over I. And this trick can also be applied here to make all of these decisions in expected logarithmic time. So let's say 6 and 9 turn out to be children of 4, and the rest turns out not to be. And let's say the next vertex to be requested is 7. Now things are more difficult since we already have some information. So for instance, we have excluded 7 as a child of 4, so the parent of 7 is now uniformly distributed only within the remaining candidates. Let's say it's 2. And concerning the children, there's a similar complication where we know 9 to be a child of 4, so 9 can no longer be a child of 7. And you'll have to read the paper for details, but roughly speaking, if we store the vertices for which we know parents or for which we know all children in a search tree with rank and select queries, then you can address these issues with polylogarithmic overhead. To summarize, I've sketched how to obtain a local access implementation of the Chinese restaurant process, which involved achieving local access implementations to various other processes as well. So for instance, we've considered the process with anonymous customers, which was linked to simple birth and death processes, and the process on a single table with customer IDs, which was linked to random recursive trees. I've not explained how to put everything together, but this is not actually particularly difficult. Right, I hope some of that was interesting, and I hope to see you at the conference.